Welcome to lectures 9 and 10 of Comp 19512 Introduction to Computer Systems. Today in the lecture you'll be filling in a unit school questionnaire, so I'll leave you to do that in the lecture. The next area we've got to look at is looking at the last lecture presented. And what we're going to do in Q3, as usual, is look at a number of areas to remind ourselves about a number of key topics that we covered during that lecture. So the first question in Q3 and Q1 is how many buses normally connect the processor to the primary memory, and then name them. So if I give you a few minutes to think about that. So in this construct of how many buses normally connect the processor to the memory, how many buses are there then? Well, there are 3 buses in all, and that's aligned to a particular types of data transfer on each bus. The first bus really should be the address bus, because the processor puts out the address first on this bus, and then via the control bus he tells it, the memory that is, that this is a valid memory, and he enables that with a control line going high, which is enable line going high. The next thing that happens is, depending on if you're reading or writing, the data will either be placed on the data bus by the processor if we're writing to the processor memory, or if we're reading from the memory will place the information on the data bus. And then it's again a control bus line which will go high if it's a write line, or high if it's a read line. So there'll be at least 3 or 4 control lines. So in answer to the question how many buses, there are 3, and the names of the 3 different buses are address, data and control buses. Let's move on to question 2 then. So how many buses are required for a typical memory write cycle? And that's not really including the clock, though everything is synchronous with the clock. So the next part of the question is name these buses involved in a typical memory write, and then state the order the buses or control lines follow when performing a typical memory write. E.g., this implies the order that the buses or control lines become active, and that means they normally go high. Simplistically, necessitates order to write data. So what is the order the control lines really start, if you like, performing a function? So I'll leave you to think about that a minute. So there's actually, in the case of a write, there's 4 different buses that are used, be they multiple line buses or single line buses. So let's name them for part B. There's the address bus, there's the address enable control line, there's the data bus, and there's the memory write control line. So what sequence would these follow then? Well, if you remember, if you're answering this in an exam, the best thing to do is actually not write this down the way I've got it down here first, but to draw a diagram and then write this data down. So what's the order? And that is verbally, if you like. So valid address is first placed on the address bus. Then next, a control line called the address enable is pulsed high, which is in, if you remember, the second half cycle of the clock cycle for the first clock cycle in this process. And then valid data is placed on the bus. Now, as it says is a write, that data will be placed on the bus by the processor. And this will be in the second cycle of the clock. And then another control line is pulsed high to tell the memory that we're actually writing data to it. So this is a single line, and it's a memory write line that tells the processor the direction of the data flow on the data bus. Now moving on to Q3, and this should be 3 in fact. What is a synchronous DRAM, SDRAM? So if you remember, we had enigmas with this concept, and the concept, if you remember back, was byte addressable, and how byte implies 8, and what that implied is that the address was put out on the address bus, but the information retrieved from a byte addressable memory is 8 bits on the 8-bit data bus. So what this synchronous DRAM is doing is aligning to bigger data buses and larger amounts of data words being transferred on not an 8-bit data bus, but maybe a 16, 32 or 64. And then part B of this is implicit in this question, really, is this idea of, and it's not stated here, of burst reads and writes through this synchronous DRAM. So again, implicit in this is that now we move away from 8-bit words to 16, 32 and 64-bit words. Embedded in each of those, 16 there's 2 8-bits, 32 there's 4, and 64 there's 8. So if we are reading, say, a 32-bit word, and remember we might need a few clock cycles to actually get the address cycle and the information to the memory, then we've moved on from there and said over 4 clock cycles how many data reads can be accomplished by an SDRAM. So really this is looking at the last lecture's notes to actually fully understand this question. So I'll give you a minute to think about that and maybe reflect on using last week's notes to look at the answer. So the first thing is an SDRAM is usually organized to work with 64-bit data bus. So each transfer of data is 8 bytes, 8 8-bit words, or 64 bits. And we have to remember it takes nominally 2.5 clock cycles to set up the first address, which is normally the base address if you remember. Then after that, after 4 clock cycles, we can read in every half clock cycle 2, so that means 8 data reads can be accomplished by an SDRAM over 4 clock cycles. Remember, you're reading 1 every half clock cycle. So if you're not sure about that, think about rereading the previous lecture. Now, the next thing I've got to think about doing is you've got to give me some feedback, or, well, actually not quite right, I'm going to give you some feedback on the coursework. So on Blackboard there will be a form you can fill in to apply for coursework feedback, and what you've got to do is email me a suggested time and obviously your name and email, and then after the coursework has been handed in, after I've marked it, I'll give you some feedback, and you can either do that from previous experience either singularly or come in as a subgroup. So this feedback will really be in my room first, so I'll probably tell you where that is if you're not sure, and I'll probably email you in an email if you're not sure, so I'll tell you that when you need to know. So the first thing to do is, on the website you'll see a number of time slots, and then select a time on a particular day and email me your requested time slot. So if you look at the Blackboard, you'll see that feedback booking process, you'll see this little iconic image here which will tell you about it, and then the feedback times are here which will show you this. So at the moment don't think anyone's booked any because I haven't told you about the process. Let's go through the process steps. So step 1, go to Blackboard, you should hopefully have been there before, and then go to the Introduction to Computer Systems and the Manchester Portal for Blackboard. So let's go through all the steps after step 1. Step 2, look at the subdirectory called My Assessment. Then step 3, go to Coursework. Step 4, click on the Comp 19512 Coursework 1 feedback times. Once you've done that, you'll get a list. You can select a time here, which is the view of the document you'll see, and then email it to me. Now, the first important thing to realise is Rome wasn't built in a day. Just because you've given me your work and you're going to sit down with me, if you're lucky, for a few minutes, not a day, doesn't mean that I can suddenly train you to write technical reports. It takes me 3 years to train my PhDs to do this. 3 years. I've just started with a new PhD. He's done his first report. He threw it at me. I tried to explain a few things about the process, and it's not his fault he didn't know this. One of the process steps is do the first draft in your logbook by hand, written out in pencil or pen on the paper. Now, what you might not realise, this could be one of the best feedback concepts you should understand. Don't jump in and do what you might do, maybe someone hasn't trained you correctly yet, in programming, say Java or any programming language, which is build a document by hacking by trial and error. You shouldn't do that. Now, I'll try and give you some advice in the feedback session, but as this is a video where I can give you some advice as opposed to the lecture, I'll just give you a few points. The first point to realise is to build a document properly, and I've seen companies do this. I've seen my wife's company who has 40 courses. My wife's taken 3 to 5 years to undertake all those courses. One of them has been mentoring for her technical writing skills of producing technical reports. They suggest this takes at least, again, 3 years. That's continuous mentoring. Okay, so I'm trying to show that I can't fix your problems quickly, but I can give you some quick feedback hints that will change the way you do things, will help you do things, and maybe make the process you undertake much more efficient and effective. So let's just think about what are the steps I might highlight in the feedback session. So, what I'm trying to get you to do is not write documents by spilling it into the computer, printing it out and dumping it. Done. Coursework. In industry, that wouldn't be the case, and if you work for me in industry, I'd have to mentor you, so you wouldn't do that, because you couldn't put that sort of document in front of a client, and it probably would have mistakes in it. So what sort of things should you do? And again, if I've got time in the feedback as well as showing you other important processes, I'll try and highlight this. Well, there's a number of process steps. One, the biggest process step, is think about the title. You might say, but there's only one title. No, there shouldn't be. Think about it. You might have 3 different titles, or 5. Maybe by the end of writing it, as my PhD, who's in another PhD who's in his 3rd year, he's thinking about totally changing his title now. He's reassessed the whole report. It's taken him up to 6 months to write this, basically a book, and he now thinks the focus or the themes it covers are not one of the original thesis titles that he put forward. The next thing he did is he wrote out each chapter by hand, and then he typed it in. Each stage I probably looked at it and gave him some input, and we both thought about one big issue. And this big issue does not come about by not doing evolutionary document progression. Document progression means you have at least 3 stages, normally 8. Some of his chapters we've relooked at together 8 to 10 times. Now, what does this mean? It means, again, you handwrite the first version, we'll have a look at it, look at the storyline, then you type it in, and if you're unlucky, that type in paragraphs will be spiel of consciousness. I'll tell you what this means. Spiel of consciousness implies, well, that's what I'm doing now. It's maybe not broken down into sound, reliable paragraphs that portray a storyline. So let's go back to basics for paragraphs and storylines. So, number one, let's say we've got 3 paragraphs for a particular topic we're going to explain. Now, if we look into these, each one should have a storyline that follows on. So, what does that mean? Well, it means paragraph 1 will have a theme. Paragraph 2 will follow on that theme, and paragraph 3 will also align to those themes. Now let's expand that and explain what's in each paragraph. Now, paragraph 1, to highlight the theme, will have a topic sentence. Now that topic sentence could nominally, doesn't always have to be the first sentence. Okay, so that could be an introductory sentence. So that sentence might help us to explain particular fact relating to the theme that the overall 3 paragraphs imply. So, what would that be? Well, it might be, as in my final year PhD student, an introductory sentence in his first paragraph about maybe a particular area that he's researching. So let's just read that out and see if it is a good sentence. So here's his sentence from an introduction subparagraph in chapter 4 of a thesis that we're putting together. So it says, this chapter describes the research of this thesis into the classification of patterns using their symmetry features, full stop. So I would say that's a relatively good start sentence. Could even say it's a topic sentence. The theme, you might realise, is symmetry. And that is covered in the topic sentence. So let's just move away from the techniques again and highlight what we're trying to do. Each paragraph, and we're saying there's 3, will have a theme which are aligned to the previous one. Now, if you remember, what I'm trying to get you to think about is storyline approach to writing the paragraphs, as opposed to spiel of consciousness. So, the reason I'm staying on this page a long time is I might not have all the time in the world in our feedback session to give you all this concise feedback. So the feedback then is, first, paragraph 1 is an introductory, broader scope paragraph. Sets the scene. Tells the first-time reader what you're talking about. Paragraph 2 supports paragraph 1. Evidences more information relating to paragraph 1. And then paragraph 3, as there's only 3 in this case, very short report, would be a closed down, a summary paragraph. In each one of those paragraphs there will be particular topic sentences which will highlight the main theme. So it might be the first one, introduction to this area. A theme sentence like I showed you the example from my PhD student's topic sentence in his first paragraph of a chapter. The second paragraph might have another theme sentence that gives you evidence to support the case, or narrower information which is more technical. Okay, and the third again will be a conclusion and bring it all together. Okay, so let's get back to the slide then. The slide says on it, one of the important things is, well, I'll tell you why I put this slide together. Some years ago, at least 2, had this feedback session. One of the students walked out, came into the lecture and said, you didn't tell me, I thought my marks were brilliant. The feedback you gave me, I thought I was doing really well. I'll say again, and it says it on this slide, I'll probably only give you positive feedback. Some years ago, quite a few now, a student did ask me for the full story, negative as well, and the problem with negative feedback is it's not always the best way to adapt someone's behaviour, help them move forward in process, in evolving their techniques, their understanding, their methodology. And he got rather upset and didn't really view the input as useful. So the reason I give positive feedback is it's more likely to improve your document, your report writing process. So let's look at the two types, summative and formative. First, I'll try to give you some feedback which is comparing the finished piece of work with benchmarks, and I've got a lot of benchmarks. I've got a gold plated set of documents that are really well written, really well stylized. I'll even show you a document, if you ask me, which I could give you a copy and you could see certain important things in this document. It might be an international norm. Next, formative feedback. We might try and improve the process, the evaluation, help you improve the design of the piece of work, help you improve the research. Now, one of the things I might not be doing in this feedback is showing you how to write every single paragraph. Spell checking every single word and grammar checking. That takes a lot of time. Technical authors can charge you £6 to £15 a page to do that. So, the feedback will be concise, formative and summative, and try and give you some process steps which should help you. So that's the feedback for the coursework. Moving on, what are we going to talk about in this lecture then? Well, we're going to talk about some words relating to the secondary memory, the disk. And then this term, talking about, if you like, the way they're laid out, these different memories from the processor, which has internally a set of registers that are extremely fast, running and transferring data at the clock rate, and then moving outside the processor to the main memory, RAM, which is a bit slower, and then finally to this disk, which is even slower. So this is called, this, if you can visualize that, a hierarchy. And actually it's a bit like a family tree, where the top of the family tree is the processor, which has very fast register transfer. Below that are the RAM locations, which store majority of the information where a program's running. And then below that, remember, the RAM is not permanent store, and then below that is the hard disk. So let's think about this during the lecture. Now, the learning outcomes that we should comprehend at the end of this lecture, and that'll be either explaining, listing, or things like that as context of what we're trying to highlight in this lecture. And the theory, well, the first theoretical component we're going to look at is the memory hierarchy, which is used in computer systems. And then at the end of that first few pages in these lectures, you should be able to explain what that concept is. What is a memory hierarchy? And then we move on from there and thinking about, okay, give examples of simple memory hierarchies. Now, the first thing you'll see is there can be 3 components in a memory hierarchy, or 4, or more. And if you go into the real theory, which is a bit beyond the scope of this course, you'll see there's many more layers of hierarchy in your actual PC, where Intel have a really specific hierarchy and memory organization. Okay, but we're going to look at the theoretical naming conventions and types. The next thing we're going to look at is, so how do we calculate the cost of this? Could we have a processor with a terabyte of RAM, 100 terabytes of RAM? Well, I don't think anyone in the world could afford that. Or could we have a RAM of 1 gig, 4 gigs, or with some of the Dell servers up to 20 gigs, very expensive systems? And then how big would be the hard disk? Well, the important thing then is the combination of the different components in the memory hierarchy will lead you to a particular figure, which we're going to give you an equation for, which will be the average cost of this multi-layer memory. And actually, a memory hierarchy is a multi-level memory, because there's different levels in it. Internally, there's the registers that are very fast, then the RAM that's slower, and then the hard disk, which is even slower. So we're going to look at trying to estimate an average cost for a particular multi-level memory. The next thing we're going to look at is the access times. So each one of these memories has a different access time. The standard hard disk, which has a spinning disk in it, is very, very slow, whereas the processor registers internally in the CPU are extremely fast, running, transferring data at the clock rate. Then we come upon this term that we could have another equation for average access time, which is related to this funny term here, hit rate. So what does that mean? Does it mean something like when the data that we want is in the main memory, that's good. If not, we've got to get it from a secondary memory, which is slower, and move it from the hard disk, the secondary memory, to the primary memory. And what effect does this have on access time? And then we'll see two important things. We'll see first that the access time is dependent on how big the primary memory is. Well, I'm not going to say any more. That's in the theory. Let's move on to the next learning objective. So the next thing we've got to do is, okay, let's go and look at the hard disk. So why is it so slow? What are the naming conventions used for parts of it, different areas of it? What are the naming conventions used for how long it takes to spin the disk up, and how long it takes to move the head from its park position into the right location? Well, we're going to see that the organization of the disk, and it's actually called format, and it's a bit like mapping an area of disk, analogous to putting streets on a ground for a city in the right locations to have houses on it. So the data is the houses, but they're put in particular areas on the disk which have two particular naming conventions which we're going to introduce. After that, we're going to see, to get to each data location on the disk, we need to realize there's two different norms for, if you like, delay of getting there. So one's a seek time and the other's a latency. So we'll look at these naming conventions and explain what they mean, the seek time and the latency. Now, we can calculate some values for this and start calculating a number of important factors that will tell us how long it takes to find the data. And this is all directly related to the rotation speed of the hard disk. Now, if you've ever looked at that, you should be able to look at the manufacturer's specifications. You'll see most disks spin at 7.2 k RPM, or 7,200 revs per minute. And this will lead us, with that rotation speed, to be able to compute this latency value. So finally, one of the things we're going to look at is a removable permanent store, which is a CD or DVD, and we'll look at how they're arranged as well, and look at some of the naming conventions, the sizes as well, and look how it stores the data on these disks. So let's move on then. So we're going to explain and calculate some different figures. We're going to look at memory hierarchies, average costs of multi-level memories, and access times for these. And then we introduce some naming conventions for hard disk, and we look at some theory behind CDs and DVDs. So the first thing we're going to look at then is this idea of maybe the third level in memory, which is the secondary memory. And this secondary memory in an end-user computer, a PC, is there to actually provide a number of functions for this computer. One of these could be that it's cost effective, so you don't want a hard disk that costs thousands. It'd be too expensive. The next thing is it's a permanent store, and the naming convention that relates to that is non-volatile storage. And that is for the software programs and for the data that they process and hold. So the important thing about understanding the secondary memory is it's a support system for the main memory, because the secondary memory retains all the software and data that's actually loaded into the main memory. So when the program runs, it's running from and in the main memory, so the program will be running and processing the data which will be stored in the main memory. So the important thing to realise about the secondary memory is it's implemented in mass storage. So the secondary memory is normally an order of magnitude bigger. So the figures nowadays, they used to be a couple of years ago, a gig for RAM and maybe 1 to 8 gig for hard disk. So mass storage devices, they should be not too expensive, that relates to cost effective, and they should be large, they should be able to store large amounts of data. These are normally implemented at present time, because they're very cheap, in hardware that's called a hard disk. And then there's a removable type of mass storage which is relatively cheap, called CD-ROMs and DVDs, and we'll talk about those a bit later. So the first thing we're going to talk about in this concept is memory and a hierarchy. So if you remember, I pointed out that hierarchy could be viewed as a sort of, not very good analogy, family tree. So the first thing we're going to look at is how cost effective is this set of components, and how do we balance it? Do we go really all out and get a very big primary memory that's really expensive, because then the processor and programs and processing the data will run really fast? Well, if you can afford it, you would do, but maybe we can't. Maybe what we do is get a reasonable cost and balance all of these: the primary memory, size and cost, and the secondary memory, size and cost. So we're going to look at these concepts now, and we're going to look at the amount of storage, and due to that amount, the cost of actually buying that amount of memory. Now let's move on from there, and then we finally look at performance. So we have a number of memories, and this hierarchy is related importantly to this concept of closeness. The closer the memory to the processor, the faster it normally is. So now you're getting a visualization in your mind, which you'll see in a diagram in a minute, of this idea of a processor. Then right next to it is the primary memory. Then a bit further away is the secondary memory. So you're getting this idea, oh, so that means that the hierarchy is more than just a number of sentences that goes CPU registers, primary memory, secondary memory. Well, not quite. That's not the best description. So you're getting this idea of distance from the processor. The nearer it is, the faster it may be for transferring data. The further it is, maybe it goes on a system bus that's slower than the internal clock of the processor. So we've got this idea of proximity to the processor, and the nearer it is, the faster it is, and maybe the smaller it is, and relatively expensive in terms of, and here's quite an important concept here, costs per bit. So we're going to bring that up in a minute. Now the further away, like the secondary memory, they tend to be slower, but much, much larger than the primary memory, and also cheaper when we relate cost per bit. Now you're seeing that cost per bit can be quite useful when we can see the cost per bit for a RAM or primary memory will probably be different for a cost per bit for a secondary memory or hard disk, where this cost per bit for the secondary memory will probably be orders of magnitude cheaper. Let's go and have a look then. So here's a three-level memory hierarchy, and it's three-level because it's got a cache, primary memory and secondary memory. So the diagram depicts this very well as a hierarchy. At the top of the hierarchy is the processor with a set of registers. Next to it, closest to it, is a cache, which is very, very fast, and then next to that is the primary memory, and furthest away is a secondary memory or hard disk. Now, below this diagram you can start seeing the amount of information that might be stored in each of these components, and you can see the furthest right has the largest amount and the processor the smallest. But interestingly, this processor, when it's interacting between and moving data between the registers, is the fastest. So it's probably running at the clock rate, the system clock rate, and it's probably only storing a few bytes. Now if we move away to a very fast cache, which normally sits between the primary and processor, which is faster than the DRAMs, which are probably static RAMs and very, very fast, we'll see that first the cache is 512 megabytes, and they're running at 5 nanoseconds. And the next level down is the primary memory, the main RAM. And that's much bigger than any of the previous storage. It's 2 gigs, but it's running much slower than the previous two. It's running at 50 nanoseconds. And then finally we move out to the hard disk, which has to spin a disk round. It's very, very big, in this particular case, 160 gig. But look how slow it is. It's orders of magnitude slower than the primary memory. It's going through this an access time of 5 milliseconds. So now let's start comparing these. So we looked at these figures for particular memories, and we saw for 256 DD-RAMs with a particular coding it was £15. So if we divide this price by this, we get 0.0586 pounds per megabit. So that's price per megabit. And then if we go to a 512 megabyte DRAM, which is at this case of this point in time that I accessed it, 2650, we see that that is 0.0518 pounds per megabit. So that's interesting. So this is, remember, the price divided by size. So it's 15 divided by 256 megabytes. And then we get the value in pounds per megabyte. Now if we move on to the hard disk, you'll see a dramatic drop in this figure. So let's have a look. We've got a 160 gig hard disk, secondary memory, and it's running a spin speed on its spindle of 7,200 RPM, revs per minute. And that costs, given a particular date when we looked it up, £42.25. So that means the cost per megabyte was 0.000258 pounds per megabyte. It's much, much cheaper than this DRAM. So now you're starting to see the price differentials for the cost of memory per megabyte. And you see the hard disk is extremely cheap per megabyte. Now let's move on. Now if we start looking at CDs, and a nominal CD is 650 meg, and if we have 25 for £2.70, that gives us a very small cost per bit, or pounds per megabit, 0.000166 pounds per megabyte. You can see CDs are even cheaper than the hard disk when we're comparing them for price per megabyte. Then if we go to a DVD, it's a bit larger, it's 4.7 gig, and we can see for this price given here for 8 of 50p, it's again 0.000129 pounds per megabyte. It's really cheap. Now let's move on. Now let's look at a different example. We've looked at a 3-level hierarchy. Now let's look at 2. This is the standard sort of diagram you'll get in a number of books. Now remember, there isn't one Bible on computer architecture. There's lots of different books with lots of different views, and they will give you different paragraphs of themes of storylines about the theory and different diagrams depicting how the hierarchy can be viewed. So here's one. Let's look at another one, and this is from Chalk's book on Computer Organisation and Architecture, an introduction. So what we're talking about here is the main memory, it's connected to the processor, and the secondary memory. So let's look at it another way, from another book maybe, and we'll see a 2-tier memory has a primary memory connected to the processor, it's nearest to it, and a secondary memory. In this book, it's called a hard disk. Now the naming conventions we're going to bring online are M1 is the primary memory, M2 is the hard disk or secondary memory. So M1 is the nearest to the processor, M2 is the furthest. Now the next bit of statistics we're going to be interested in is the size of the memory. So M1 has a size of 1 gig for this example. M2 has a size of 160 gigs. Now the next thing we're going to look at, which we were talking about implicitly in the previous slides, is the access time for T1 relating to M1 is 50 nanoseconds. So 50 nanoseconds to access data in the primary memory. But the cost for for this memory, for this size, is £53. And if we go to the secondary memory, we'll see that the access time for T2, relating to M2, the hard disk, or secondary memory, is 5 milliseconds, much, much slower than the primary memory. And the cost is $42.25. So you can see it's cheaper, larger, but slower. So now you're seeing you have to balance these when you buy a system or design a system. Now we're going to say that these two are the same, main memory and primary memory, DRAM, secondary memory and hard disk, M2. Depending on where you read about this, they'll give them slightly different naming conventions. Now the next thing we're going to be interested in a minute for calculating the average access time given this two-layer hierarchy is T1 compared with T2. So this is T1 and this is T2. But remember, T1 relationship to size, it's 1 gig as opposed to 160 gig. So this one's 160 times bigger than this. So if the program or data is bigger than that, 1 gig, you're going to have to read it in multiple chunks of information. And then we're going to relate what this access time means. So 50 nanoseconds is 50 times 10 to the power of minus 9. And 5 milliseconds is 5 times 10 to the power of minus 3. So you can see that this is actually 6 noughts different to this. It is much, much faster. Now let's start looking at these memory costs and comparing them. Let's first take a sum, an aggregate, and we're going to call that total memory cost of M1 and M2. We're going to use the naming convention M1, M2. Memory M1 costs £53 for 1 gig. Memory M2 costs £42.25 for 160 gig. So if we add those two numbers together, the total memory cost is $95.25. So now we're going to try and formulate an average memory cost. So let's look at that then. So we've got to remember this formula then. And the formula is the average memory cost is the cost of memory 1, we've just done this, plus the cost of memory 2. So that will be that figure there, over, divided by the size of memory 1 plus the size of memory 2. So this is a formula which you might expect for the average memory cost. So let's have a look at that. And that's in per gigabyte. So it's pounds per gigabyte. So here we are then. We've got M1 plus M2, which is this figure here. And then we've got the sizes in gigs, so we're just going to write the gigs and take it implicitly that these two numbers are in gigs, these two numbers are in pounds. So again, first on top of the division sign, M1 is 53 plus M2, which is 40, cost using this equation, given this price per memory M1 and M2 and the size of M1 and M2. Okay, so note these average are in gigabytes for the memory size and in pounds for the amounts. Maybe if you're in America, those would be in dollars. So the trick is really remembering it's pounds or cost divided by size, okay, for the average memory costs relating pounds to gigabytes. Now what we're going to do is move on to the other specification factor for a memory, which is access time. And that relates to reading and write data to and from the primary memory. And we're going to remember the naming convention is M1. So, if the process is reading data that is not in M1, now we've got a problem. If it's not in M1, we have to go and get it from the other memory. So we have to go to the secondary memory. We're going to call this M2, if you remember. So it goes to M1, checks if the data is in M1. If it's not, it goes to M2. And then what it does is it takes the data from M2 and stores it into M1. And then the CPU reads from M1. So this is actually a very time-consuming process. It checks in the main memory. If the data and the program it's sequencing through are not in the main memory, M1, it has to go to M2 and get the information. And then it moves it into M1, and after it's done that, the processor reads it from M1. So you'll see, ooh, that's a massive time constraint because we're going from nanoseconds in the main memory to milliseconds in M1. So what does this have as an effect? Well, let's recap. M1 had an access time of 50 nanoseconds, and that was called T1, which is relatively fast. But M2 is slow, and that's T2. So T2 is 5 milliseconds, much slower than 50 nanoseconds. So if we get the time to go through and access via T1 to T2, we have to add 50 nanoseconds plus the 5 milliseconds for the access time for the hard disk, and then we get a value of, if data is in M2, remember we first had to access M1, which is this one, to check if it was in there, and we found it wasn't. Then we've got to go to M2. So the access time is nominally 5 milliseconds plus 50 nanoseconds, so it's 5.000405 milliseconds. So this is 10 to the minus 3, and that's 10 to the minus 9. So let's get a figure for this access time. We're going to call it the average access time, which is dependent on M1 and M2. And in fact, it's dependent on the proportion of time that we reference data in M1, the data's already in M1, as opposed to going to M2. So let's read out this sentence because it's probably quite important. So, the average access time depends upon the portion of memory references that can be serviced by M1, that actually means they're in M1, rather than M2. So what does this mean for this average access time calculation? Let's look and see. First, the lower the average access time, well, let's relate it to an equation and start thinking about this in a minute. First thing to realize is we're going to bring into play a particular naming convention. That naming convention is related directly to M1. It says if the data is in M1, we've hit the data and we want to know the hit rate. So we'll explain what that is in a minute. So what we're talking about here is some ratio that tells us how often we hit on the data in M1 as opposed to having to go to M2. So let's move on. Now we've got this concept of hit rate is aligned to addressing M1 and the data is in M1. So hit rate is the number of accesses serviced by M1, primary memory, divided by the total number of accesses. Okay? So we'll look at these figures in a minute to try and give you an idea of that ratio of number of accesses serviced by M1 over total number of accesses. Let's look at it in this blank box. So you're going to have to write this down in the lecture. So H equals number of accesses serviced by M1 over total number of memory accesses. So let's think about this then. So H is represented, as you can see here, as a ratio, and this ratio ranges from 0 to 1. So we're going to give you some typical examples of this so you can start understanding how this hit rate can be calculated and see and get some insight into what this means given a certain number as a hit rate. So if you're looking at it percentages, if we have a 70% of the memory referenced are serviced in M1, so let's just relate what that means. That means when the processor goes to M1, the data is actually there, and 70% of the memory references are all in M1, and obviously the other percentage, which is 30%, has to be accessed via M2. So this means you can either relate that to a 70% memory reference are serviced in M1, or it's a 0.7% hit rate. That's 0.7 of the time you're actually accessing the data in M1. Now let's give you an equation then. So here's the equation using the hit rate, and it's called the average access time. Now this is for particularly the example we've shown with a two-level memory system, and that consists, if you remember, of M1, fast memory, which had a 50 nanosecond, 10 to the minus 9 access time, and the slower memory M2, which had a 5 millisecond, 10 to the minus 3 to the power of minus 3. And if we have M1 service 90% of the memory access, we could use this equation. Okay, so this would be quite easy to use then, because we just put in here 0.9 for the hit rate, and then T1 would be this figure and T2 would be this one, so that the average access time T subscript AV would equal T1 plus T2 times 1 minus the hit rate. Hit rate of 90% here would be 0.9 here. Okay, so the figures we would have would be equal to 50 nanoseconds plus 5 milliseconds times 1 minus h, where h is 0.9 in this case. You can do this as well for the 3-layer system, but we're not going to go into that at the moment. We'll move on from there. So this is the formula you'll probably have to use in the exam. And this one's for a 3-tier system, but you can actually see it's just an extension of this equation. So let's move on from there then. So now we're going to give you some examples. Given particular hit rates, 50% is 0.5, what is the average access time? So let's go and do that. So using this equation of T average equals T1 plus T2 times 1 minus h, we sub in these two values for T1 and T2, and then we sub in this hit rate, 50% is 0.5. So you can see, translating this symbolic representation, putting in the values, these are the values we get, and then we'll get these numbers in, which leads us to an average access time T subscript AV of 2.50005 milliseconds. Now what happens if we start changing the hit rate and say there's more data in the primary memory that we need so we can access it? Well, what happens is the hit rate can go up dramatically, and this has an effect on the average access time. So now we've got 90% of the data in the main memory, and that's related to a hit rate of 0.9. So let's use this equation again. So it's T1 plus T2 times 1 minus h, put in the numbers, put in the new hit rate, and you'll suddenly see T average 500.05 microseconds. With a hit rate of 0.9, the average access time is an order of magnitude reduced on a hit rate of 0.5. So let's take it all the way up and say all the data, we hardly ever, once we've loaded it into the main memory, access the secondary memory. So we've got a 99% hit rate, most of the data, nearly all of it, and the program is in the primary memory, so it's got a hit rate of 0.9. What effect does this have? Straight away, we've gone through these calculations before, we change the hit rate to 0.99, we can see that the average access time is 50.05 microseconds, orders of magnitude faster than this. So if most of the data isn't in the primary memory, then the average access time is very, very slow. But as soon as it is, we can actually see that this means that the average access time is very, very low when we're hardly ever accessing M2, and always, majority 99%, accessing M1. So this is a very good equation aligning to hit rate for assessing the average access time of a two-level memory. Now what we can note from this is that as the hit rate increases, the average access times falls. So that says the more often you access data that's in the primary memory, the faster your access rate, or the average access rate, the time taken to do that, will be much, much faster, and that time will fall, as we've seen from the examples. So if we have a hit rate of 0.9, it's 100 times faster than using M2. okay, on its own. So it's very, very fast. So let's start looking at the hard disk then. We've looked and given us some metrics and some details about the main memory and how we can allocate some average access time, its speeds, their size for the primary and secondary. So now we're going to move on to the hard disk and start talking about it. In the lecture I'll probably show you the hard disk and pass it round, and you'll see straight away that the hard disk is made up of a number of spinning disks. These spinning disks are coated with aluminium, which is magnetizable material that can store information. So let's have a look at this then. So bits are stored in this case on the hard disk surface as polarized, very, very small polarized areas, which basically polarize that very small area to point in a north or south direction, 1 or 0. So these are called magnetic domains, and what it actually says is you're setting up information. A 1 points that tiny bit of information, a magnetic domain, in one direction, north, or the other direction, south, is a 0. So data is stored on disk, and it's either written or read to the disk, and a head flies over the surface to write and read the data from the magnetic storage material. Now the important thing that you might have gathered is the disk rotating at quite high speed, 7,200 revs per minute. Okay, now you can see some people when they pick up their laptop, if they pick it up and juggle it around where I've got this hard disk in it, you might crash the head, so it's probably not a good idea. So let's move on then. This is a very good diagram of a hard disk. It's looking at it from the side. You can see the spindle that the disk rotates about. These are the hard disk cylinders that rotate, and these are the heads that read and write from and to this magnetic material. So the first thing to realize is that this storage media has multiple plates. Each one contains data. So as you can see, they're normally labeled surface 0, 1, 2, 3, and they're double-sided, two-sided, and you have two heads to read, and the arm moves backwards and forwards across the heads. But from this view, the side-on view, you don't quite see how the disk, the information, is placed on this circular disk, which is the format. So now you can see this is a multi-plate disk, has a number of heads. These rotate. Let's look at it in another view. Now we're looking at it from the top down. We're going to introduce two naming conventions for finding locations of information. So the first is, and in fact the organization of the information, are concentric tracks. So this is organized in a number of tracks, and they're actually on each plate, there are many tracks. Now each track is then subdivided into sectors. So there's many tracks, each track is subdivided into sectors. Normally in its legacy that these tracks, which are then subdivided into sectors, the sectors are normally 512 bytes. So these subsections, sectors on each track, are 512 bytes. So you can see now how the data is stored. It's broken down onto tracks, then the tracks are subdivided into sectors. Each sector is normally a size of 512 bytes. And you can read or write to specific sectors on specific tracks. And you'll need to know, once the disk has been initially formatted, the location, so there will be addresses for each track with a specific sector for data. So now let's talk about this organization and what consequences it has. So as the organization of the data is laid out in tracks and sectors, if we're reading and writing data, what happens? Well, the first thing to realize was we must spin up the disk and then find the data. So we're going to have to move the head to the right location. This takes 2 steps. And this might be quite an interesting question because it's quite pertinent to how the disk actually works. 2 steps for this process. Number 1 in this process steps, the head must be moved to the correct track. So if you remember, the format, the topology, the layout of the disk is a number of circular tracks on the disk, and those tracks are then subdivided into sectors. So the head is first moved to the correct track. So if you write this down in the lecture, this empty box will have some information in it. So this is known, getting to this correct track, as the seek time. Okay, so first the heads move to the correct track, and that's a particular time called a seek time. Now step 2 we must wait and then move round. So the cylinder itself will rotate, be at the right track, and it's taken a particular time, the seek time, but it then has to rotate to the correct sector. So I'm just going to read this out again to make sure you get this explicitly. 2 steps to finding the data for reading and writing on a hard disk. The first, the head must be moved to the correct track. And this time to do this is known as the seek time. Then, once we're on the correct track, we must wait until the start of the sector which we need to read or write data from or to. And we have to move to this when the disk has rotated to it. And then it locates it under the read-write head. So this is quite important, these 2 steps. Find the right track, find the right track and then sector. So the track has a seek time and the sector has a rotation latency. Okay, so you've got to move the head into the right track and then spin the disk round to get to the right sector. 2 times associated with these: seek time, rotation latency. Let's move on to this and say normally the data which we may want is randomly distributed across the disk, across the sectors and tracks. So what on average is a seek time? How could we work out a figure to calculate this? Well, let's just say that it takes nominally 1/2 of a disk radius to rotate to the correct location. So let's read that paragraph to highlight what we're talking about. Seek time. If the data is randomly distributed among the disk sectors, the seek time is, on average, the time taken for the head to move 1/2 of the disk radius. So let's look at some typical values then. This can be, this time, between 5 and 10 milliseconds. And this is referenced in one of the course books. When the data is adjacent to the track, that means it's right next to, this can fall to 1 millisecond. So if you remember back to the previous lecture where we saw the concept of data in memory and accessing memory bytes, multiple memory bytes, if they're right next to each other it was faster for access. Exactly the same happens if the data and the tracks are right next to each other. This seek time can dramatically drop from 5 milliseconds to 1 because it's just another rotation of the cylinder. But first you have to find the right location initially. So there's considerable benefit then from reading and writing blocks that are stored sequentially, one after the other, or successive sectors on adjacent tracks. So if the data is next to each other, it can be very fast. And in fact, that's what happens when your disk is defragmented. It moves all the relevant data for a file which could be distributed across the disk next to each other, so they're in adjacent tracks. Okay, so that's what is important. They're trying to speed up the access of the data. So that's all related to the seek time. So the seek time is dependent on how fast the head can be moved backwards and forward across the disk. So it's moving from track to track. Okay, and that's the seek time. Now in your lecture we'll have a break now. So moving on. So let's talk about latency then. So latency, well, what is it? Let's look at the concept of an average for this. So what we've got to do then is wait for a rotation of the disk to move to the right sector. We're on the right track. If you remember, you first move to the track, then you move to the sector. So let's say nominally on average you'd have to take half a rotation of the disk to start reading. Say that's nominal. So you get the right track, move the head in, and then rotate the disk nominally half a rotation on average. What does this mean then? So let's see what this means. Given, let's take an example. So if we're given a nominal speed, and this is most disks in the world spin at this speed, 7,200 revs a minute. Okay, and that comes back from the lecture we saw when we put together a system for our end user PC. Okay. So, how would we calculate this latency then, given that spin speed? Let's look at it on the next slide. So first, the first step, because this average latency we're going to calculate takes a number of steps, given 7,200 RPM, we take the 7,200 RPM and we divide it by 60. So we move from revs per minute to revs a second, revs per second. So it's 7,200 divided by 60, and then we move into revolutions per second. And that, once we've undertaken that calculation, is 120 revs per second. That's step one. Now step two, if there's 120 revolutions in a second, that means there's 1 over 120 in a second. So one revolution takes 1/120th of a second. So we divide 1 second by the number of revolutions. That's 1 divided by 120, and we get for one revolution takes 0.008333 seconds. One revolution, 0.008333 seconds. Now remember, if you remember a slide back, we want to do half of that. So the third step is we take half of this. On average, we're going to wait half a revolution. So we take half of this value, so it's 0.008333 divided by 2. So this gives us a value, the average latency, because that's the three steps we've been going towards to calculate this value, is 0.004167 seconds, or shift the decimal place 1, 2, 3 places, 4.167 milliseconds average latency. So to calculate the average latency takes three steps. First, take the spin speed of the disk, 7,200 revs a minute, divide it by 60 to get the revs per second, 120. Second, find out how many and how long it takes for one revolution. So if there's 120 revolutions in a second, that means one of them is 1 second divided by 120. So it equals 0.008 approximately seconds for one revolution. Now the average of that for one whole revolution is nominally half a revolution. So we divide this figure by 2 and we get 4.167 milliseconds average latency, the time it takes once we've selected the right track to move to the correct sector, which is halfway round the disk nominally. Now what we're going to do is look at how the system controls this information transfer. We're going to look at the disk and its controllers. So what does this mean? The hardware, the mechanisms, the bits of hardware that control interactions between the hard disk and the main memory and the processor. What do they have to do? And well, it has to do quite a lot. So the first thing it has to do, it's connected to a bus, and then on the bus we have a disk controller which has and is able to interpret commands. So the processor will send to the disk controller which is on our bus, we've seen already, commands which will tell it to either read or write. So first we have to ask, or the processor will, the data to be read or written to the disk. One of the first things we might do when we initially use the disk is format the disk, which we've seen now is laying down a particular pattern of tracks and sectors in a particular topology on the disk surface. So let's add this blank here. So formatting is the first thing that establishes on the disk surface the location and the addresses of these sectors and tracks on the disk. We also have error as well, so we have a capacity for dealing with error checking as well. So now you've seen that the controller, as well as reading and writing data, will also have to initially set up the format of the data that's allocated across the disk surface, and that's called formatting, which sets up this ways of putting and laying down data on each surface, and we've called them sectors and tracks. So this is done by a disk controller by writing to registers. So there's going to be a number of registers which we have to write to and from. We'll probably deal with them in another lecture, but what it actually does is it memory maps certain information from the disk to the main memory. So what we're talking about here, we'll just read through this to make sure it's explicit. The processor controls the disk controller by writing to registers provided by the disk controller that are mapped into the computer's address space. So the concept here of the computer has an addressable memory, particular location in that memory has a set of registers for the disk controller. Now we'll move on from that and maybe come back to that in a minute. The next thing we're going to look at is the makeup, the fabrication, the layout of a CD. So these are optical storage where they encode data and they burn them onto the surface, and this is done by a laser. And normally if they're copying them, they're just pressed really. So this is a side view of the disk where you can see there's two different components to the data. There's pits and non-pits. So the data is encoded and there's certain layers of hardware that make up this CD. So these areas, the pit is normally coded as 1 and the land, where there's no pit, is encoded as 0. So the data is stored in 1s and 0s in little pits or lands across the CD. Okay? Now how would we get the data from the disk? So how would we read it? What we actually do is we put a laser above this and spin the disk, rotate it, and see if there's a land or a pit below the laser. So what actually happens is these are actually, the pit depth is about 1/4 of a wavelength of the laser light. When we encounter a pit here, we see that the light reflected back to the laser receiver will be destructive. So we can actually tell, the laser can tell if it's on a pit or on land, just by what happens to the return light. So these optical detectors then can shine and scan the disk and tell if it's a 1 or a 0, a pit or a land. So that's quite important. If you want to see how this works, you could go and look at this URL reference. So that's a side view of a CD. Now this is what they actually look like from the top. So when you start reading, you start at the very heart of the disk and you spin round in a ever increasing spiral and read the data. Okay, so the disk spins a particular speed. They can be as fast as 530 revs a minute, or they can even be slower at 200 revs a minute. So you can see that this media, the CD, is much slower than the hard disk. So it takes even longer to write data to this disk, or even read. And it normally spins at a variable rate depending on where you are on the disk to get the read-write access time. So it could be spinning in between 530 and 200 RPM. So these are actually relatively large storage devices. They're 650 megs each one of these, and it's also stored, the data itself, along with some error correcting as well. So a CD will typically, in a particular format, be able to read and write data at 153,600 bytes per second. It's relatively fast. Now if we look at the CD mechanism, so we're going to look in the heart of the machine, we'll start seeing when you put a CD in, you put it into the disk drive, and down here this head moves backwards and forwards, which, as you remember, will find the track, and then it will spin round and find the sector. This is a laser that basically emits light onto the CD, and the amount that's reflected will tell this receiving device if it's a pit or if it's a land. So let's have a quick more look at the dimensionality of this. So CDs will run sometimes at a faster speed than we've just talked about. So they can run up to 52 times faster than a standard spin speed, which we've just seen. So if it's 52 times the data rate we've just seen, let's just go and have a look at the data rate. The data rate we've just seen was 153,600 bytes a second. So it can run faster than that. Particular CD players can run at 52 times the standard data rate. So this can run at a very large or very high bytes per second data transfer, approximately 8 megabits a second. So if it's running at 52 times standard spin speed, it's running at 8 megabits a second. So we've looked at the data transfer right there, and what actually happens is this die layer, if you make a read-writable one, is changed. So we can get a laser which can actually change the surface and control the reflectivity, and you can make them transparent or reflective by subjecting this read-write material to a laser light. So if they're copy disk, which are the previous ones we've talked about with pits and lands, that would be just a readable data item. If you want a read-writable, a rewritable or recordable media, the way it does it is by changing the reflective index of the surface of the CD. So let's look at the next portable recording media, and that's DVDs. The way they get the density of the DVD up is they have multiple spirals. So as you can see, with one layer, single-sided, single layer, you get 4.7 gigs. If you have single-sided double layer, you get 8.5 gigs. If you have double-sided double layer, you get 17 gigs. So DVDs can vary in dimensionality for storing information. To do this, you'll probably need shorter wavelength lasers. You'll also need tighter spirals, and you'll need very small pits. And the DVD is a digital versatile disk. So this leads to information, and this sort of disk can store 133 minutes of video stroke sound for a standard single layer, single-sided disk of 4.7 gigs. So these are quite useful storage mediums. So if we now compare DVDs and look at the speeds of DVDs, we'll see that the standard speed transfer rate is 1.4 megabits a second. And then if we do 16 times that, we get 22.4 megabits a second. So let's do some compare and contrast for the different capacities and wavelengths for CDs and DVDs. And we'll see the dimensionality for the track pitch between each track is 1,600 nanometers. And then we can see that that is opposed to 740 for a DVD. So you can see that DVDs have much closer together tracks. Then if we look at the dimensionality and what this relates to in storage of information for movies, we'll see that single-sided single layer is 4.38 gigs, which is 2 hours, and if we go to the maximum double-sided double layer, it goes to 15.9 gigs, which is over 8 hours of movie time. Now if you review your lecture when you've got time, think about any questions you can ask me. The next point, we're going to look at the next area in this lecture, and that'll be inputs and outputs, controlling the inputs and outputs. So let's look at the learning outcomes from this half of the lecture. The first thing we're going to do is explain this simple term of processor interaction with a device on the bus. And these devices are called I/O devices. They're called input-output devices because they're sitting on the bus that the memory is sitting on as well. So that memory hierarchy I showed you is not quite the case. As well as the memory, the different types, the primary and secondary, there's also I/O devices sitting on this bus. So we'll have a look at processors and how they might talk to these I/O devices, interact. And then we'll see one of the ways of interacting between I/O devices is to actually write a program to do it. Might not be that efficient, but we'll say that's a sequence of instructions that's setting up for the transfer of data between the processor and the I/O, the input-output device. So we'll talk about programmed I/O. So, input-output. So what actually happens on this bus that we might have naively given you the view that the bus is only connected to the primary memory and the secondary? Well, it's not. It's actually also connected to a wide range of other devices called input-output, mainly because they're inputting data to the machine or outputting data from the machine. And we'll look at these in a second and name them. So these include mass storage devices, which we've seen, could be CDs or DVDs. Now the way you should actually think about these input-output devices is, how do you think we get the data to the machine? Input-out devices are typified by keyboards. We type in keys, characters that build words, and we review our data by viewing them as monitors via a screen, a cathode ray tube, or LED flat screens, or plasma. Then you've got the mouse, which I'm using now, which can interact with the screen and make it an event-driven system. So these are human interface devices, which are actually input-output devices. So the way they do it is they communicate on a bus. Other devices that communicate on a bus are communication devices like network cards and modems. So they will also be connected to the bus. So here's a diagram depicting the systems bus. Now, previously you may have thought that the processor was only connected to the main memory and the hard disk. Well, that's not quite the case, because actually in between the hard disk and the processor is an I/O device that will control the interaction between the processor and the hard disk. You're going to have to go through this device to tell it, if you're reading and writing, but also tell it, give an address where the data is being placed here and probably here. So then if you're inputting data via this pointer, you're going to use this I/O device, which will be reading the location and then drawing it on the screen. Keyboard I/O will be monitoring the keys and monitoring if any is pressed and then decoding them. The monitor will be displaying, well, it's displaying this screen in a memory and then scanning it all the time and displaying it in front of you. And then you might have permanent storage via DVD recorders, and maybe reading and writing data via and to the internet via a modem to subnets. And again, each one of these will have an I/O module which will be talking the right language for each of these sub-devices, and each might have different protocols, rules and ways of interacting, which they do. So the first thing to realize then is each I/O device interfaces to a particular type of I/O behind it, and there might be more than one device. These devices are made up of hardware and software that runs the interactions between the processor and these different devices, and maybe putting the data into memory or into non-volatile or volatile storage here and non-volatile here. So let's look at how we control a particular I/O device. The processor itself will access what's called a register in the I/O device. So this is an example of an 8-bit register. And this 8-bit register is exactly like a memory location in main memory. So the first thing to realize is each I/O device or controller has a set of registers, and they'll be given specific names. So we're going to name them in a minute. So these registers themselves have to be addressable by the computer, and this is where the term in a minute, memory mapping and a memory addressed, will come into play. So a register is memory mapped, or is a location in the memory of the CPU via the memory. So this register is capable of holding maybe one or more bytes depending on the size of the register, and this will be placed at a particular or unique address, in the memory. So let's go and have a look at where this register will be placed in a minute. So now what we've got to look at, this idea of, well, let's give you an example. Let's talk about a simple device. We're going to read the keyboard, and the keyboard itself will transmit or send a single character to the computer. Now if we do this, one of the ways we could do this is use the processor to do all the work. So in terms of speed, if we let the processor do all the work, it might be slow, but let's just go through and show you what that would be like. So the processor can do a lot of the work and wait for a character to be pressed, so it could keep scanning the keyboard. So here's the keyboard and a key would be pressed. So how would we deal with this then? Well, first let's name the particular types of register. There's two registers we're going to use for a keyboard. One's the status and one's the data. So if we interrogate these words on their own before we go into the theory, status tells us something about the I/O. So status will indicate something, whereas data will maybe be the data word we're going to read, in this case a key coding. So let's go through first and look at what a status register is. So a status register indicates the status of the keyboard if a key has been pressed. So how does it do that? Well, it only needs one bit in its status register to say one of the keys has been pressed. So let's have a look at that in detail. What's the norm is the function of the status register says one of the bits, and it's the least significant bit, is used to tell us the status. So it says if this bit is set to 1, then a key, a character, has been typed. If it's set to 0, or cleared after a character has been read, then it's set and says no character has arrived. So 1 tells us that a character has been typed, and that will be decoded into the data register, the actual number, after we've read the status register. And if this is set to 0, if we interrogate this status register and look at this bit, then no data or no key has been pressed. So let's go and have a look at the next register. The next is the data register. So once the key's been pressed, you have to decode what that coding of that particular key is, and that's done by normally two different types of coding. One is the ASCII 2, which is 256 possible characters, and these are encoded as an 8-bit coding. Java tends to have 16-bit Unicode standard, a bit more complex, a few more symbols it can use. So let's look at one particular sequence of key presses, H-E-L-L-O, hello. One of these encoding for the H would encode to a data register loading this coding 01001000, and that's equivalent in ASCII 2 to an H or H character. Okay, so this bit pattern coded in ASCII 2 represents the key press in a particular position of H. So this coding for hello would actually come out as an ASCII 2 coding of 72H, 101E, 108L, 108L, and 111 for the 0. So that's the sequence of key presses when they're coded to ASCII 2 characters. And they will be placed sequentially one after the other in the data register. So now let's look at this concept of, so how does the CPU read the status register first to see if data or a key has been pressed, and then the data register to get the actual numerical value of the key? Well, this works by a concept of locations, particular addresses. So this diagram that's going to appear in a minute is called a memory map. So where would we place these? Well, let's just assume that the status register is placed at memory address hex FFFF0000, and the data register is placed right next to it, the data register address at FF0004. So if we place this in the memory map is a linear sequence of addresses, probably starting at 0 and going in this case to all F's. So let's visualize it now. Here's a memory map for the whole memory given these number of bits for the address bus. So it goes from this base address up to this address. So these locations of these two registers are basically here, which is the status register at this address, and here above it for the data register. So now you can see that memory mapping is breaking down the memory into locations where different parts of information is stored, like the primary memory, or different I/O through the registers is accessed. So you can see that the processor only has an address bus, but the address bus can get to and read and write data to and from RAM, or I/O devices which can transfer data into this memory addressable location via two different types of registers. So first we would read a status register of an I/O device and say, are you ready? Or has, in this case of a key, has a key been pressed? If so, we would then move on to the data register and read the data register, and that would give you the numerical representation of the key coding, in ASCII 2 probably, for the key that has been pressed. So that's memory mapping. So we've got two steps for reading a character then. First, the processor needs to read from this first address here, which is a status register address in the memory mapped hierarchy of the memory that we've set up. And then if it reads a 0 in the least significant bit, actually no character needs to be read. If it reads a 1 in the least significant bit, we need to read a character. So move on to step 2. Then it reads the character from the address of the data register in the memory map, and it'll probably then store that in main memory. So the IR module itself will then clear the status register, this bit which was set to 1, it will clear it down and reset it to 0, so it will actually then be ready for another key press for the next key to be typed. So two-step process for reading a character from a keyboard. Now there's a number of ways of doing this. One of the ways is programmed I/O. That means the program that controls this transfer of data is totally handled by the CPU. So that's why it's called programmed I/O. It will run a program to interact between the keyboard and the CPU. So we assume that it will spend a lot of time reading from the status register address and saying, has a key been pressed? Has a key been pressed? Has a key been pressed? So it'll spend most of its time here if it's a programmed I/O, which could be wasting time. Once the key has been pressed and the least significant bit has changed from a 0 to a 1, we go to the next stage and we read the data register from this address, and then we store the data in the data register of the keyboard I/O into a main memory location, and then we go back to this checking the status register loop. So here we see that this is really called, programmed I/O is called polling. It keeps polling the status register and saying, has a key been pressed? Has a key been pressed? Has a key been pressed? So it polls the status register of the keyboard I/O. Now, importantly in this is that if we do this programmed I/O using polling, we'll see that we spend a lot of the time waiting and checking the status register. Could be a bit wasteful. So really, if we move on to particular operating systems like Windows, we'll see that what we really want to do is run other processes at the same time and not be always checking the keyboard. So really it's important to realize that it doesn't make any sense at all to keep checking the status register and spending all the time waiting when you could be doing something else useful. So the preceding flowchart showed that we don't actually spend much time just reading the character. Most unuseful time is spent checking the status register. Maybe that's not a good idea. So let's look at another way of doing this. One of the ways we could do this in a different way is say, well, why don't we do this by periodically checking? So we just read it once. If it's not there, we don't stay in the loop and check the status register. We exit and go and do something else. So we could periodically check for programmed I/O, and then once we've done this, we can only move forward and check the data register if the least significant bit is set to 1. If not, let's go and run some other program. So this flow process is quite important, that we could poll the I/O and not stay in the status register loop. So the code to read from the keyboard must be called on a regular basis in this previous page's flowcharts case. Now we've got a problem here now, is if you call it more frequently and there's no character, could be wasting time. But if you don't call it enough, if you call it less frequently, you could, well, what would happen? Well, you might have to wait for a while before the CPU accesses the keyboard that you've pressed a key. Okay? So normally you might have a keyboard buffer, but if the keyboard doesn't have a buffer, you've got an even worse probability that you could actually have a queue of characters which, once the keyboard buffer's full, you could start losing characters. So the problem with programmed I/O when it's looping and checking the status register would probably be handling it fast enough, but if you move to the second form, where once it's done a status check it exits the programmed or polled I/O, then we can see that this polling, which is infrequent, could be not a very good idea. So let's review our whole lecture then. The first thing to look at then is we looked at secondary memory by first looking at hierarchies. We looked at a 3-tier hierarchy and we said a number of things about the hierarchy. The hierarchy tells us which is the closest to the main processor. Then on from there we saw that the hierarchy had a sort of familiar sort of layout. We had the faster registers are inside the processor, then we go to the next fastest memory, in this case it's the cache, and then the next, which is primary memory, and then the slowest, which is secondary or hard disk, which is driven through an I/O device. And then the important things we thought about this hierarchy was, first, this one had a few bytes of storage, but they're very, very fast. 0.25 nanosecond access time, whereas the cache was a bit slower but still fast, 5 nanoseconds, bit bigger storage capability, 512 megabytes. Then we moved to the main memory, which had 2 gigs of memory, but now only running at 50 nanosecond access time. And then we had this large storage device, which when the power turned off would have the memory in, whereas these would not. So it's 160 gig in size, but it's running very, very slowly at 5 milliseconds. Then we started looking at the cost of comparing and balancing these memories for maybe a 2-tier memory for M1 and M2, when we said the cost of this one, M1, and the cost of this one. And then we looked at dividing this by the size, and then we could work out the average cost of a 2-tier hierarchy. Then we moved on from there and said, okay, if we've got a 2-tier hierarchy with this processor accessing the primary memory and only sometimes accessing the secondary memory, if it accesses this, it hits the data, that's good, so we'll call that the hit rate. And if it does this at a very high hit rate, say 0.99, it will hardly ever access the secondary memory. And then we had a formula for this. It was the average access time is T subscript AV equals T1 plus T2 times 1 minus H. So T2 times 1 minus the hit rate. So that gave us a measure of the average access time given that we had a particular hit rate for this main memory that said we had a particular amount of the information in that main memory. And then we started looking at the different types of storage, permanent storage from the hard disk, and how it had heads and spinning cylinders, and there was on each cylinder tracks and sectors. And then we moved to DVDs after we'd initially looked at CDs. Then we looked at different types of I/Os. We looked at a particular I/O and said most I/Os have registers. For an I/O talking to a keyboard, we've got 2. A status register that tells us if a key's been pressed. Once a key's been pressed, the key decoding is placed in a data register. So we have a sequence of operations we have to do. One of the ways of doing it was programmed I/O, where we had to read the status register, check if a key's been pressed, and then read the data register. If not, we'll stay and check the status register. And then the other one, we'll talk about that another time. If you have any questions, let me know your questions. So this is the end of the lecture. The only other thing I could advise you to do is look at the Q3s for next week, and they will help you at the start of the next lecture. This is the end of this lecture.